What if the secret to life's origins wasn't in the sky or the sea, but beneath our very feet? For decades, scientists believed that plate tectonics Earth's massive. Shifting crustal plates only began operating around 2.5 to 3 billion years ago. That's already billions of years into Earth's history and well after the earliest signs of life. But recent studies are challenging this long-held belief, pointing to compelling evidence that plate tectonics may have started within just a few 100 million years of Earth's formation, possibly as early as 4 billion years ago. If true, this shifts our entire understanding of how Earth evolved, and it opens up a new theory that plate tectonics wasn't just a geological process, but a biological catalyst that made life possible. Let's go back in time. Earth formed about 4.54 billion years ago, born from the chaotic debris of the early solar system. For a long while, our planet was a molten ocean of magma, bombarded by asteroids and inhospitable to any kind of life. As the planet cooled, a solid crust began to form, and eventually, continents and oceans appeared. The traditional view has been that, for the first 1 or 2 billion years, Earth's surface was relatively stagnant, a kind of stagnant lid. Tectonic system with no plate movement, very little recycling of crust, and a largely static outer shell. This picture made sense given the limited geological record from such a deep past. But new evidence paints a much more dynamic portrait of early Earth. In Western Australia's Jack Hills region, scientists have analyzed ancient zircon crystals, some of the oldest minerals ever found on Earth, dating back to around 4.3 billion years. These zircons bear isotopic signatures that suggest they were formed in conditions involving repeated heating and melting, exactly the kind of thermal cycling you would expect from plate movement. Meanwhile, rocks in Greenland and Canada show magnetic anomalies that can only be explained by the presence of shifting land masses, continental drift as early as 3.8 billion years ago. Combined, these data imply that plate tectonics may have been operating much earlier than previously thought, possibly from the time Earth's crust first solidified. Why does this matter? Because plate tectonics isn't just about earthquakes or mountains. It's a planetary scale engine that regulates Earth's temperature, recycles essential minerals, and creates diverse environments such as hydrothermal vents, shallow seas, and landmasses where complex chemistry can unfold. These processes are crucial in the formation of amino acids, nucleotides, and other organic compounds believed to be the building blocks of life. In fact, the earliest microfossils, tiny microbial life forms, date back to about 3.5 billion years ago, and they are often found near ancient hydrothermal systems, which are directly tied to tectonic and volcanic activity. Moreover, plate tectonics plays a fundamental role in Earth's carbon cycle. Subduction zones, where one tectonic plate slides beneath another, drag carbon-rich sediments down into the mantle. This carbon can be re-emitted through volcanoes, balancing atmospheric CO levels over millions of years. This balance helps maintain a stable climate, something that is absolutely essential for sustaining liquid water and, by extension, life. Without this long-term thermostat, Earth could have become a runaway greenhouse like Venus, or a frozen wasteland like Mars. In this light, plate tectonics might not just be beneficial to life, it might be essential. There's also a growing body of theoretical work suggesting that the very existence of stable continents depends on tectonic movement. Continents act as chemical incubators, concentrating minerals, moderating climate, and creating unique surface conditions where complex organic molecules can form and evolve. Without tectonics to form and renew them, Earth might have remained a water world, with no solid ground for biology to anchor and diversify. However, this new theory is not without controversy. Some geophysicists argue that the early tectonic activity might have been significantly different from what we see today. Instead of the dynamic global plate system, with rigid plates and well-defined subduction zones, the early Earth might have experienced what's called protoplate tectonics. In this model, surface motion was more chaotic, governed by hot mantle plumes pushing up localized sections of the crust, rather than entire plates moving in unison. These movements may have resembled tectonics but lacked the structural coherence and recycling mechanisms of today's system. Even so, the presence of any kind of surface mobility at such an early stage still supports the idea that dynamic geology played a critical role in Earth's habitability. One particularly fascinating hypothesis links the onset of plate tectonics with the rise of atmospheric oxygen. According to this model, subduction-driven recycling of oxidized minerals could have helped produce and sustain oxygen in Earth's early atmosphere, eventually leading to the Great Oxygenation Event about 2.4 billion years ago. This oxygen boom was one of the most transformative periods in Earth's history, paving the way for complex multicellular life. If tectonics helped initiate this event, then its role in the story of life is even more fundamental than we thought. In the broader context of planetary science, this discovery has implications beyond Earth. When we look at exoplanets' worlds orbiting other stars, one of the signs we search for is tectonic activity. Why? Because if plate tectonics is linked to habitability, then planets with Earth-like crustal movement might be the best candidates for hosting life. That means studying tectonics isn't just about understanding Earth's past. It's about finding life elsewhere in the universe. So what we're seeing now is a paradigm shift. From passive early Earth to a young planet already churning with internal energy, recycling its crust, and maybe laying down the tracks for life to ride. Plate tectonics isn't just geology, it's planetary alchemy. A process that may have taken a sterile rock and set the stage for consciousness to emerge billions of years later. As we uncover more from Earth's ancient rocks and refine our models of planetary behavior, the mystery of life's origins inches closer to clarity. And in that mystery, the ground beneath us, shifting, restless, and alive may hold the answer we've been searching for all along.